Here we go. Testing. Testing. It's horrible. Try a different microphone. Testing. 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 Input level is not high enough. All right. It's getting something. Okay. I have to go back. Come on. Testing. That's horrible. Testing. That's better. Come on. Okay. Well, we'll make lemonade. All right. Any problems with the material from chapter 1 and 2 that we need to discuss first? We have one. Yes. Oh, the extra credits. You can hand them in to me, or if you forgot and left them at home, you can dump them in Brightspace. That's a good idea. Yeah, if you take a picture of it, it kind of loses something unless you're good at image manipulation. I don't think anybody's in the CIA here, are you? Or now the FBI. Okay, so let me open up the last set, chapter 3 PowerPoint. Let's see, where are they? Got to get them going first. Yep. All right, let's do it this way. Yeah. And then make a slideshow. Now. Oops. Oh. Okay. Got to do things in the proper order. I'm going to share the screen. There it is. Now I can slideshow it. Come on. There. Okay, it is sharing. Okay. So one of the technical problems I'm having today is I can't get that TV on. So the guys in the back, you're going to have to use your binoculars. Huh? I'll speak as loudly as possible. Chapter 3, Atomic Structure in the Periodic Table. I finally got hold of my periodic table. Well, we found it on the floor, and I rehung it. So I've got a reference point there. Let's see. So I can do it this way. Okay. Today we're going to dig into the structure of the atom and use that information to tell us something about several things, actually. The structure of the periodic table is based upon the structure of the atom. And once we know these things about the atoms, even down to the electronic configurations of the atoms, then it starts to become clearer why certain elements react and some don't, or why they react in a certain way. Like some of them will make ionic compounds, some of them will make covalent compounds. And once you know the electronic structure, it makes more sense why they prefer that method versus the other. Right now, we just have the general rules. Metals and nonmetals are usually ionic compounds. And nonmetals and nonmetals are usually covalent compounds. But once we know something about the electronic structure, then we can say, and not just that, but trends on the table, the way the trends run. And I'll explain that in more detail later. So let's move to a little history. What do we know about the atom? Well, in the early 19th century, John Dalton, who was a British scientist, proposed a model for the atom, a model for matter, actually. He proposed an atomic model that is, and it's partially based upon the ancient Greeks. They were trying to figure out in 4th century BC, Greece, what matter was composed of. But the ancient Greeks weren't real big on experimentation. I mean, they were great at memorizing stuff and they were great at doing problems in their heads. But it seems like the only ones who wrote anything down were the poets. Well, Aristotle and Plato, they wrote philosophy. But they didn't experiment too much. They just proposed things and thought about it. So, and they proposed that all matter, some of them did, just a few, proposed that all matter was made of an elementary particle they called the atom. And they called it the atom. It's based upon the Greek words. This prefix, anytime you see an A in front of a word, it means not. It means the opposite. And this is based, TOM comes from the Greek, which means to cut or to divide. So it's not cut. In other words, you can't cut it any smaller. That was their name for the elementary particle. Their problem was that they said that all matter was made up of these elementary particles, but every kind of matter was made up of the same particle. And so then they sort of painted themselves into a corner. You still hear me? Okay. I know we're serenaded by jackhammers today. So by proposing that everything was made of the same atom, they had difficulty explaining why we had so many different substances. And it wasn't until John Dalton came along and he proposed that everything is, yes, made of an elementary particle that you can't cut it any further. He didn't know about subatomic particles then. But he said that every element, and we had isolated, by his time, we had isolated a handful of elements. He said every element is made up of an elementary particle called the atom, but the atom of this element is different than the atom of that element. So that solved the problem that the Greeks had. They went into all kind of mental gyrations trying to figure that one out. Never came up with it. Maybe that's why so many of the ancient Greeks didn't buy into the atomic theory at that time. Anyway, so John Dalton said matter's made up of these elementary particles called atoms, but that's where he stopped. And then we come to J.J. Thompson, who was he was an Englishman. And by that time, people were starting to play around with electricity, mostly static electricity and batteries. And they knew the difference between positive and negative charges. And he said that the negative charge originated in the atom, which was kind of a earth-shaking proposal, because if the negative charge originated in the atom, that means that there was more to the atom than that you could see on the surface. And if the negative particles came from the atom, then there also had to be positive particles in the atom, because atoms were neutral. They knew that. Okay, so J.J. Thompson actually was able to determine the ratio of the mass of what was later called the electron and its charge. So he had a charge-mass ratio that he had published. That was in the early part of the 20th century. And then not too long after that, another Englishman, Ernest Rutherford, was opposing the model, the model that was given for the structure of the atom, which incorporated negative and positive charges. And it was something like that. They just said the negatives are all over here and the positives, equal number of positives. What's that? 2, 4, 5. I need one more. Okay. So, and they call it the plum pudding model, because if you've ever had plum pudding, you've got these little bits of fruit scattered throughout. And there doesn't appear to be any structure to it. Rutherford said that it rubs him the wrong way. So he proposed another model, and he called it the nuclear model. By this time, we also had surmised that the mass of the electron was very small compared to the atom, because if you let electrons escape from atoms and they charged ions, the mass that was left behind was almost the same as before. So the electrons that were leaving and being captured and measured had to be very, very small in mass. So where's all the mass? Right? Rutherford said it's got to be in the positive charge. So that, in addition to, he just didn't like the plum pudding model. He proposed a model where all of that mass that was left behind was located in a central region of the atom, a dense nucleus. So his model, the nuclear model, was his answer to that question. And then he set about to prove it. And I think we're going to talk about that, aren't we? Let me look ahead. I don't want to steal my own thunder. No, I don't have a slide on it. Okay, so Rutherford set up an experiment. And the simpler the experiment, the better. Because simple experiments have less, you have less opportunity to misinterpret them. We call it elegant. So Rutherford set up an experiment called the gold foil experiment. And at this time, there were also researchers working on radioactivity. And they had identified basically three types of radioactivity. There was the alpha particles, which were essentially helium nuclei. Right? No electrons, just the nucleus. But they were originating from within the atom. Then there are beta particles, and they are essentially electrons, but they're moving at very high speed. And they knew they were coming from the nucleus because of the consequences of radioactive decay. That's in a nutshell. And then there was gamma radiation, which was essentially high energy light. Okay, so Rutherford decided that if he was going to probe the atom with a particle, his best bet would be to use the helium because it was so massive. So he took gold foil, and he knew that gold foil could be hammered very thin, just a few atoms thick. And that's ideal because if you have too many atoms in the way, the beam, when it hits your gold, is just going to get stopped. Right? He wants it to be able to pass through the atoms, or if the occasion arose, to actually strike the nucleus. So with his gold foil, right? Everybody knows that's the symbol for gold, correct? Gotta at least learn that one. I mean, gold is good. And then he had a source here, an alpha source, that shot a beam at that gold foil. And he had to make sure it was straight, right? So he used a collimator. Basically, a collimator is two slits aligned like that. Right? So if the particles are coming out like this and they're kind of at an angle, then if you only use one slit, you might get some going off like that. But if you have two perfectly aligned, then the only ones that are going to get through that are traveling in a straight line. So his beam hit the gold foil, and on the atomic level, he said, here's what he said would happen. If the plum pudding model were correct, then the beam would go straight through, right? Because there was no concentrated mass anywhere. It was all scattered throughout. And if anything, it would diverge a little bit. So the plum pudding model said his detectors out here would have basically, they would detect the beam there. If his model were correct, then what he would get he would get strikes over here, here. A lot of them would be there for sure, but they would be scattered around here. And in fact, he had detectors behind. And he said sometimes those alpha particles would strike the nucleus and they would be deflected large, and some of them would be bounced almost straight back. And that's exactly what he found. So when Rutherford did his experiment and published his work, the plum pudding model was dead. And now we know the atom's structure is essentially a nucleus with the positive charges in the middle, all the dense matter there, and then the electrons are out here somewhere. Let's see, 3. Okay, let's balance it. But we didn't know what they were doing out there. We just knew that that was the separation. Well, there was also, let's see, I think I painted myself into a corner. I wanted to say something about neutrons, because when we talk about isotopes, we need to know about neutrons. What they also realized, other scientists realized, was that for most of the atoms, the protons in the nucleus did not account for all the mass. So there had to be another particle in there that did not have a charge, because they'd already counted for all the charge, right? The negative and the positives. So there had to be another particle in there that accounted for the rest of the mass, and that's the neutron. And my mind's gone blank. I can't remember whose work that was. Chadwick, yeah. Actually, Chadwick was an understudy, student or an associate of Rutherford, and he took that ball and ran with it. And Rutherford got a Nobel Prize for this work, and Chadwick got a Nobel Prize for that work. Okay, so now that we know we can account for all the mass, and the nuclear model is the proper, the accepted model for the atom. Now we want to know something about its structure. And without going into too much detail, because we don't have that much time, now it comes to just a few years later, actually, Niels Bohr. Have you ever heard of Niels Bohr? That's okay. He proposed a planetary model for the electrons around the nucleus. Right? So these electrons would be positioned in discrete orbitals around the atom. And the more energy the electron had, the further it is from the nucleus. So the lower energy is here, the more negative, actually in mathematical terms, it would be closer to the nucleus, its energy value. And if it was completely removed from the atom, okay, if we ionize the atom, then this distance out here is infinity, right, as far as the nucleus is concerned. So Niels Bohr proposed this, and he based his energy levels, which we could calculate for the hydrogen atom only. When you start getting the bigger atoms, then you get interactions that really mess up its formulas. So it's based on the hydrogen atom or hydrogen-like atoms, and I'll explain what I mean by that in a minute. But what he noticed was that when an electron was elevated to this level, it absorbed a certain amount of energy to get there. You got to add energy to make it jump to a higher level. Okay, and very often that's in terms of light, and it had to be exactly the right amount of energy. And I'm going to use an abbreviation here that we haven't described, but I'll explain it to you. Energy, obviously, it's E, and that's H nu. This is a Greek letter nu, and nu stands for frequency. So the frequency of the light times this constant, which is Planck's constant, and you don't have to remember that right now. I'm not even sure if I'll get to it anyway. But what I'll do is there's light coming in, and then I'll say, okay, so that's what that means. That's energy. So if you add energy to that electron, it bumps it up. Well, Bohr came up with a formula. Actually, he came up with this one. That said this amount of energy, this exact amount of energy, will promote the electron from one energy level to the next. If it's more than that or less than that, it won't work. It's got to be exactly the right amount. And if that promoted electron drops back to that same energy level, it'll give off that same amount of energy in the form of a light beam. And then you can measure the amount of energy that's being given off by measuring its frequency, multiplying by Planck's constant, and there you go. So this was a start toward understanding how the atom was constructed. So we knew that the electrons were occupying various energy levels. It's just that Bohr was starting the process, but this wasn't the end of the story, because electrons don't behave like planets, right, in orbits around the sun. They just don't do that. It was just lucky, fortunate, that this model worked for the data that was available. Later on, Erwin Schrodinger, who's the last one in this slide, came up with a set of equations that were largely, well, they were based upon waves, right? Light can be viewed as either a wave or a particle. And depending on what you're measuring, it appears as a particle or it appears as a wave. That's called the duality of light. And it was a controversy for a long time until scientists finally said, we give up. It's both, right? And we've come to realize that every atom, every form of matter has particle characteristics and wave characteristics. Each of you can be written down as a wave function. It's just that it's not very significant because of our mass is so large and we're moving very slow. To have a significant impact on our wave character, we'd have to be moving really fast, like 3/4 the speed of light or something like that. And I'm never going to do that. But for small, very small particles, it's a significant factor. So electrons have a wave character, and Schrodinger used that information and his mathematical skills to develop this series of equations that eventually became quantum mechanics. Now, you're not going to have to learn what quantum mechanics, you're not going to have to manipulate any equations. For one reason, I can't do it either. But it just means that now we have we're getting closer to reality. And actually, the wave equations are based on probability. So when you solve these equations for the energy level of your electrons, then you can't say anything about where they are. Okay. And let's see, do I have that slide in here? No, I don't. I'm touching on a principle called Heisenberg's uncertainty. Heisenberg's uncertainty principle says just that. At this level, where you've got really, really small particles moving at high speeds, the act of measuring influences the particle itself. So if you want to say where it is, you can't say what its energy is. Actually, he said you can't say what its momentum is. That's mass times velocity. Has anybody had physics in here or physical science? Okay. You remember momentum? What's momentum? Mass times velocity. I think it's, they use the Greek letter rho. That might be density, I'm sorry. But that's momentum. So what Heisenberg said was, mass is not going to change, so you can't know how fast it's moving. You can't know anything about its energy if you know where it is. If you identify what its energy is, you don't know where it is. Okay? So he kind of stuck. But that's the history of the atom in a 20-minute spiel. Okay, so now we know that atoms are made up of protons, positive ones, electrons, the negative ones, and neutrons, no charge. And the proton and the neutron are essentially the same mass. Neutron's just a slightly bit heavier than the proton. And we've discovered from studying radioactivity that those beta particles, the high-speed electrons, when they come from the nucleus, they are signaling a change of the neutron to a proton. So there's a little bit of mass that's lost from the neutron. Now it's got a positive charge and it's a little bit less mass, it's a proton. You don't have to know that. I just throw that out there for those who are interested. Okay, so this slide illustrates, it's probably hard to see from the back of the room, illustrates the difference in masses. Now, the protons and neutrons, electrons, they're all small. And that's so many grams. Right? The unit of measure you see there is grams. But the key point here is look at the difference in the electron and the proton. Focus on the powers of 10. Okay? The power of 10 for electron is minus 28. The power of 10 for the proton is minus 24. So in the sciences, we have a term. Well, actually, it's not a term, it's a phrase called order of magnitude. Anybody ever heard of that? It essentially refers to the powers of 10. So the order of magnitude is what size is the power of 10. When we compare these two together, 10 to the minus 28 and 24, how many orders of magnitude different are they? 4, right? 4 orders of magnitude bigger is the proton by mass, which means when we say 10 to the 4th power, what is that in standard notation? All right, 1, 2, 3, 4. 10,000 times. So the proton is 10,000 times more massive than the electron. Okay. And similarly, the proton. Notice the proton is just a little bit bigger than the neutron's a little bit bigger than the proton. Okay, so there's your nucleus. It's got, well, hydrogen has only 1 proton. And if I didn't say it before, because I teach several chemistry classes, it's kind of hard to keep track of where I left off with one and start with the other one. If I didn't say it before, the number of protons determines the element. That's the atomic number. I think I do have a slide on that, so I better not steal my own thunder. So a nucleus is a small, dense, positively charged center of the atom. Right? Rutherford proved that. It contains all the protons and all the neutrons in the atom. The atom overall is neutral. Right? Unless you force it, it will stay neutral. And that's because the number of protons in the nucleus equals the number of electrons in this cloud outside the nucleus. Okay, so those are all the subatomic particles. And now, let's see. All right. We use a letter Z to represent atomic number and a letter A to represent mass number. Now we need to define what they are. But I like it better this way. When you write your symbol, you're learning all these symbols for the elements. When you write the symbol, and I'm going to use a generic symbol, just an X. And I use an X because there's no X up there. You can't be confused with anything. Well, xenon has XE, but just 1x, there are 4 positions around this symbol that are reserved for specific information. Okay. The Z position here, that's the atomic number. And that's equal to the number of protons. Okay. This position is reserved for A. That's the mass number. And that is the number of protons plus the number of neutrons. Okay? So if you know both of these, you can find out how many neutrons there are in that isotope. We haven't defined isotope yet. We will. So if you got this number and that number, you just subtract this one from that one, and that tells you how many neutrons you have. We only put numbers in these positions when we need to discuss the internal structure of the element, or whether we're talking about one isotope versus the other. Normally, when we're writing symbols in chemical formulas and putting them into equations, we leave these out. Because if we know the symbol, it's easy to find the number of protons. Just look on the chart. Find the symbol, and on that chart, the red numbers to the lower left of each symbol, that's the number of protons. That's the Z number. But if a question comes up on a test and it refers to these values, then you know they need to go in there. Otherwise, and later on when we're writing compounds and we're writing, well, we've already done that. When we write compounds and we write chemical equations, then you don't need to put these in there. The other 2 positions. If the atom is neutral, you can either write a 0 up here or just leave it blank. If it's blank, we assume that it's neutral. But if it's an ion, if it has lost electrons or gained electrons, then we'll put the charge there. Right? So if it's sodium and we make an ion out of it, it's always +1. Right? And that's one of the trends in the table. If it's out of that first column, the alkali metals, in ionic compounds, they always are +1. The second one, the alkaline earths, they're always +2. So if you have an ion, that's where you put the charge. If it's a halogen, it'll be a -1. Okay. All right. So we got one more position down here. Guess what that one's for? That's the number of atoms. Okay. It could be the number of atoms in a diatomic or triatomic or octatomic element, or it could be the number of atoms in a compound. If we write water, right, we know that there's 1 oxygen atom, 2 hydrogen atoms in that molecule. Okay. And we never write 1. That would be redundant. Right? If the symbol's there, you got to have at least 1. So when you're counting up atoms, like if you have a question on a test that says, how many total atoms are in this formula? Don't forget the ones that have no subscript. That's a 1. Okay. All right. So now we've got our territory staked out. And the next slide sort of animates all that stuff, right? In case you want to go look at it again. There's sodium example, right? So sodium has 11 protons and 23 protons plus neutrons. So how many neutrons does it have? 12, right? 12. 12 in that isotope. I might as well define an isotope. An isotope is the element that has a variable number of neutrons. So this isotope will have so many neutrons. That isotope will have a different number of neutrons. It won't have a different number of protons. What happens if we do that? You get a different element. Right? Okay, we can't do that. And for that reason, when we make ions, what changes between, say, the neutral atom and the ion of the atom? The electrons. The only thing that can change is the electrons, right? If we change the protons, we've got a different element, right? So don't shoot yourself in the foot by changing protons. Okay. All right, so that's an element. It's a pure substance that can't be broken down any further into simpler pure substances by chemical means. So during a chemical reaction, the element will not change. It'll be the same element before the reaction as after the reaction. The only way you can make new elements or create new elements is in a nuclear reactor or in an atomic blast. Okay. You got to start playing around with the nucleus and the subatomic particles to make new elements. Okay, so now we know that pure substance as an element is composed only of atoms of that element. So they all have the same number of protons. Now, Dalton said that the atoms in an element were identical. But we know now that that's not true. They may be chemically identical because they have the same number of protons and electrons in the neutral state. But they may have different number of, did I say protons and electrons? They may have different number of neutrons. Right? So Dalton was wrong there, but we can forgive him because he didn't know about neutrons then. Okay. Oh, that's a good point. That's why we know that all the atoms in a pure element have the same chemical properties because they have the same number of protons, the same number of electrons, and consequently, they will have the same electronic structure. Okay. I mentioned isotopes already. The key there is the different number of neutrons. So if you're at, let's see, what was that? Sodium at 11 and 23? What if we say potassium, 19 and 40? Can those be isotopes? They have different number of neutrons, don't they? But can they be isotopes of one another? No, they have to be the same element to be isotopes. Okay. I'm just making a stupid point to hopefully drill it in. Okay. So they will have the same chemical properties and physical properties, but the physical properties might differ a little bit. And actually, we use those physical properties to separate the isotopes. When everybody heard of the Manhattan Project, right? That was the project that was set up actually in Manhattan to ultimately create an atomic weapon. They had to move it to a more remote location. So they had several places set up in the country, and everything came together eventually at Alamogordo, New Mexico. But the supply chain for everything that went into that site was scattered all over the country. When I was a kid, we lived in Oak Ridge, Tennessee, and we had 3 massive government-owned plants, and their sole purpose was to figure out how to separate U-238 from U-230. Oops. 235. Well, 2 of them were, 2 of the plants. I think the third one might have been dipping their toes in the plutonium well. But you can't separate these chemically because they have the same chemical properties. So you have to use their physical differences. right? This one's more massive than that one. So we used that characteristic to separate them. And one plant was set up as a gas diffusion plant. So it would convert these to uranium hexafluoride, which was had a lower boiling point. You try to boil uranium, you get a lot of energy. Uranium hexafluoride would boil at a fairly low temperature by comparison. And then you would take that mixture of gases and you would shove it through a sieve with very, very tiny holes. To make a long story short, the ones that go through the fastest are the lightest ones. So this would go through faster, and on the other side of that sieve, you'd have an enriched amount of U-235, only it was like a fraction of a percent. So you had to have stacks and stacks and stacks and stacks of these things. And the building itself covered like 100 acres. It was massive, just so they could hold all of those sieves. But at the end, you had virtually pure 90% U-235. And all you had to do then was reconvert it to the metal, and you could make a bomb out of it. Nowadays, we don't do it that way. It's more efficient to use ultracentrifuges. Right? So the centrifuge will spin these gases, and the heavier ones will move to the outside, and the lighter ones will be on the inside, and you just suck them off and send them to the next one. You have banks of centrifuges. That's what Iran is doing right now. They've got their ultracentrifuges running full time, and Biden and his administration are oblivious. They don't care. Anyway, the physical property is how you separate. Okay, so here are two isotopes. Silicon, we know it's silicon. You just look on the chart, right? And you'll know that the periodic tables is from small numbers at the top, they get bigger toward the bottom, and from left to right. So just follow along until you find number 14. And, excuse me, that's right. I was looking at sulfur for a second. Silicon has 14 protons. And one isotope has 28 nucleons, we call them. Could be a proton or a neutron. And the other one has 29. So that means the first isotope has 14 and the second isotope has 15 neutrons. So they're the same element, different isotopes. Okay, the mass number of this element is what? 51, right? 23 plus 28, protons plus neutrons, 51. Okay, what element is it? What do you need to know to find the element? The atomic number, the number of protons. So 23, just look up on the chart. So follow along until you find 23. What is it? Did I have you memorize that one? Vanadium. Vanadium. Is it on there? Yeah. Okay. Okay. So now, when you look at the periodic table, each one of those little boxes has the element, has the atomic number, it has another bigger number, usually in the upper left or upper right-hand corner. And that number is the atomic mass, not the mass number. The mass number is always a whole number because it's the sum of so many protons and so many neutrons. The atomic mass is a weighted average of the masses of the isotopes. And the isotopes can have a mass number that's whole number, but the individual masses of the isotopes will not be the whole number. The reason for that is we need some reference point. One of the elements we have to set as a value, and everything else is related to that one. And the one that we chose was carbon. That isotope is given arbitrarily a value of atomic mass units. Okay? The atomic mass unit is something close to the mass of a proton, but it's not exact. But that's our reference point, right? Infinite number of zeros, that's our reference for that isotope. Right? Everything is referenced to that. So all other isotopes, even other isotopes of carbon, will have a different atomic mass. Okay? So the idea is that if we're going to do chemistry and we need to know what's the mass of our element in that reaction, we have to take into account its mix of isotopes. Okay? And for carbon, it's mostly carbon-12, okay? And there's a little bit of carbon-13, and there's a very small amount of carbon-14, and there are others, but they're insignificant. So for the chemist's purpose, we need to have a weighted average, right? It's going to be pretty close to 12 because most of it is carbon-12. And then it'll be a little bit higher than 12 because there's some 13 in there. And the 13, for argument's sake, we're going to assume that the mass of, well, obviously carbon-12 is 12, but we're going to assume that the mass of 13 is 13. Right? It's not exactly, but for argument's sake, we'll use that abundance. So when I say weighted average, does anybody have an idea of what weighted average means? You ever calculated your own GPA? You're doing weighted average. Right? Because this class is worth 4 credits, right? So it's worth, an A in this class is worth more to your GPA than an A in a 3-credit class, right? Yeah, that's the idea behind weighted average. Which one has more weight in the calculation? So we would say, for this case, we would say 98.89%, which is, yeah. And that would be times 12. And then carbon, I'm using a fractional amount here, right? Not the percent value. It saves me the trouble of having to divide by 100. And then 1.11% is 0.0111. And that's times 13. And we can stop there because the other isotopes are almost insignificant. And if you take this calculation and you say, all right, the contribution of 12 is that much, that fraction of the average. And the contribution of 13 is that fraction of the average. And you get a number here and you get a number here, and you add them together and you get a number there. And that number is the number that's reported on the periodic table for carbon. And let me see. This is an old table, but they don't change a whole lot in the not a second decimal place. It's usually fairly constant all the time. They recalculate them occasionally, and they will change in about the 4th, 5th, or 6th decimal place. So it doesn't matter to us. So on this table, carbon is 12.0114. Atomic mass units. Okay. That is the sum of these calculations here. Whatever 12 times that and 13 times that, add them together. That's the atomic mass. And we could add a prefix here, the average. That's the weighted average atomic mass. And that's what they report up there. That way, when we conduct chemical experiments and we do reactions, we don't have to worry about the isotopic mixture of our chemicals, our elements. It's already been accounted for when we use that. And hopefully I'll be able to show you in a few minutes that those numbers actually have two different units that can be used. Atomic mass units for now. But that's not very useful in the lab. We need another. And hopefully I'll show that to you. Or maybe that's, I wonder if that's in the next chapter. Or maybe down the road. I'll just follow the slides. I'll tease you with that information occasionally. Okay. How am I doing on time? Okay. I'm not moving along too fast as usual. Okay, so there's the calculation on a slide. All right. So I'll do a lot of bending now today. So this particular problem is asking you for two things. What's the average atomic mass? The mass that you would find in the table for this element. If one isotope with a mass of 186.956 atomic mass units, it represents 62.6% of the isotopes in the mix. And this is in the naturally occurring mix in the Earth's crust, where we do most of our work. It might be different on some other heavenly body. Right? So that's for exochemists to worry with. And then the other isotope at 184.953 atomic mass units represents only 37.4%. So how would we calculate the average atomic mass for this one? Let's see. Yeah, speak up. I don't have a slide calculating it, so we'd have to do it ourselves. So we do what? What contribution? Yeah. Times 0.956. Yeah. And then the other one, the other contribution for the isotope would be what? Okay. So you get a value for that, add them together, and you get a number. And the number is 186.207 if you do the math. Okay. Now, can we use that information to find the element? Actually, yes, we can. Because although the atomic mass in the periodic table is not, this is bad English, is not as unique as the atomic number, it can get you very close. And most of the time, you can tell the difference between one element and the next if you have calculated the average atomic mass. So 186.207 would be what? I'll just follow along. Can they get bigger from top to bottom, left to right, just like the atomic number? 186.207. Here we go. Right on the money. And that, you didn't have to memorize that one. That one is rhenium. You didn't have to memorize it. No, I didn't think so. Now, occasionally, if you use this method to find an element, they might be very close together, the atomic masses. It doesn't happen very often, but sometimes it does. So it's not as foolproof as the atomic number. Okay. Atoms of an element that contain a different number of neutrons are, right. Okay, now we get to the periodic table. We know something about the structure of the atom. We're going to talk about the periodic table and how it is structured. Did I introduce Avogadro's law last time? No, I didn't. Okay. Well, we'll get to it eventually. The only reason I talk about it is Avogadro's law was instrumental in solving a serious problem in the latter part of the 19th century for industrial chemists and university chemists alike. Because they did all their calculations based on mass. Mass of reactants go in, mass of products come out. And when something went wrong and they didn't get the right mass of a product that they thought they were going to get, they didn't know how to fix it. Because chemistry is not based on mass. Chemistry is based on atoms. Okay. And they didn't have a handle on it at that time. So, be that as it may, we'll talk about the periodic table now. The periodic law says that the elements in the table are arranged in order of increasing atomic number. And they occupy two different formats. They can either be vertically arranged, we call those groups or families, or they can be horizontally arranged. We call that the period. We call it the period because, let's talk about the groups first. Dmitry Mendeleev is given credit for the modern periodic table. And the reason for that is he was a Russian school teacher before the Russian Revolution. Right? He probably couldn't have done this after the revolution. Anyway, he arranged the elements that were known at the time in groups that had similar chemical characteristics, particularly, and some physical relationship. So he put those in groups. In fact, the original table, the groups were horizontal. That was his first publication. Second publication, he saw the light and turned them this way. So all of those elements were in these families or groups because they had similar characteristics. And he arranged those groups in increasing numbers from left to right. And he found that if you follow along a horizontal line, say you take a group, and you go horizontal from left, then you're going to go increase from one group to the next. You're going to go one proton at a time. So these horizontal periods will go from left to right. See, there's rubidium and strontium, 37, 38, and then these get kind of messy, so we're going to skip over here. And they increase, and the chemical characteristics change as you move from left to right. So if you keep going and you get down to the noble gases and you go to the next one, like here, 36 proton, then the next one will be 37. Right? So 37, instead of sticking it way out there by itself, it has chemical characteristics that are similar to the first group. So you wrap around and you come back and start all over again. That's a period. It comes from the idea of periodic motion. Like you folks that have had a little physics, maybe in high school, you know what periodic motion is. Think pendulum, right? The pendulum's moving, right? But it's not going anywhere. It's going from here over here and then back to here. That's one period. It goes through that motion and it comes back to where it started. Same idea here. You go across one period and then you circle back, start over again. Because the groups then line up correctly. That's the overall scheme for the periodic table. Okay. There were some predecessors to Mendeleev. Dobereiner, he noticed a relationship among groups of 3 elements. They had similar characteristics, so he put them in triads, but he didn't even go any further. Lothar Meyer, these are both Germans, actually put them in tables, and he used the concept of valency. Valency was their term at that time for how reactive are they. The alkali metals were extremely reactive. The alkaline earths were a little less reactive, so they had a different valence, and so forth and so on. But that's as far as he went. Mendeleev, when he put his periodic table together, the reason he's given credit is because he made predictions. He grouped these things according to their characteristics, and if he came to a point where the next element that was known, say he went from, I can't remember the detail. Say he was looking at gallium, and the next element that was known was arsenic. They didn't know germanium. Then it should have gone here, right? But he noticed that its characteristics were more like these guys. It should go in that family. So he skipped it. So there should be an element in there that we haven't found yet. And he went one step further. He said that element was going to have a certain weight between these two, and it was going to have certain chemical characteristics. He identified them. And when he published, he said, we're going to find an element for all these blank spaces that I've indicated. And they're going to have these characteristics. Sure enough, we found them. So that's why Mendeleev is given credit, because the way he approached his periodic table was he used it to predict the existence of other elements. Oh, I was right. Actually, they didn't know gallium or germanium. He had to skip those 2. Right? And then we found the elements later. Okay, now one more person, Henry Mosley. He was in his 20s when he was doing research, graduate work, and then associate work in an English university, the details of which escape me for the moment. But he was interested in X-ray spectroscopy of the elements. Take a pure element and you fire X-rays at it, excites it, right? The electrons move to those higher orbitals, and then they jump back, and they, actually, if he's using X-rays, he was probing the nucleus. Now, come to think of it, X-rays will excite the nucleus. Okay, so it'll excite the electrons too, but it will work its way to the nucleus and excite the nucleus, and it has a structure of its own too, which we don't have time to discuss here. But when the nucleus relaxes, it gives off characteristic wavelengths of light. And he noticed that for each element, he devised this formula. All he had to do was predict the wavelength of the light that was given off, was to change the number. There's one number in there, just from the element. This one, next heaviest, next heaviest, next heaviest. All he had to do was increase the number by one whole number. Right? He would go from maybe 27 to 28. Put them in there. They would accurately predict the wavelength that was given off. That he called the atomic number. What he didn't realize at the time was his atomic number was equal to the number of protons in the nucleus. Unfortunately, around 1914 or 15, I can't remember when it was, he joined the Army and went to World War I. And in their debacle, that was their storming the peninsula or the beaches of Gallipoli in modern-day Turkey, he paid the ultimate price. So that was the end of his research. Okay, so these the periods are horizontal rows, and the groups, some of the groups or families have names. Right? So this first group, let's see, do I have a, yeah, they have different names there, and I will point out these 1A, 2A, 8A, 7A, 6A, 5A. That is an old way, the earlier way of numbering the groups. It has value, but now when I ask you to do that extra credit and fill out and create the periodic table, we use the modern way. So it's just left to right 1 through 18. But these Roman numerals have value because they tell us what the number of electrons in the valence shell of each atom is. So we'll talk about that later also. This must be an old slide because they're using the old way. Okay, so there's a periodic table that's probably hard to read from the back of the room. But each of these groups has different, some of these groups have different names. This one on the far left, these are the alkaline metals. Obviously metals. These are the alkaline earths, the second group, or the alkaline earth metals. And then all of these in here, right here in this green, those are transition elements because they transition from this side to that side. So chemists are not that creative sometimes. This, start from the other side over here. These are the noble gases, or the inert gases, because they don't react, right? They don't play with anybody. And we'll find out why that is later. If you've had a biology course that talked about just smattering of chemistry and they mentioned the Octet Rule, that refers to a perfectly filled electronic shell, doesn't want electrons, doesn't want to give up electrons. They're perfectly happy right where they are, so they don't react with anybody. Well, you can force them, but normally they don't. This group are the halogens, right? We used to have halogens in our headlamps in our cars. Now they're moving toward LEDs, but I think mine's old enough, it still has halogen bulbs. And some of these street lights or parking lot lights are halogen lights. They usually have iodine in them. But they're a -1 charge, and that's the name of their group. The next group over are the ones that belong to oxygen. Those are the calcagens, CHALCOGEN. The calcagens. And that's derived from lots of compounds. Actually, most of the metals in the Earth's crust are combined with oxygens. They're oxides. And when you form them in the lab, the ancient term for it was forming a calx, CHALX. So that's where they got their name. These are the pnictogens. And it starts with a P, but the P is silent. Kind of like my last name, the GH is silent. Sometimes we do that in English. I don't know why. But that's it for this part of the chart. These two groups and these 6 are known as the representative elements. Now, these two are extracted from this place right between lanthanum and hafnium. You'll see it goes from 57 to 72. These 14 elements should go right in there. But that would leave a big gap up here, and it would make the table, pretty wide, huge as a matter of fact. So we just pull them out. So these, the lanthanides, go right in here, and these, the actinides, go right in here. Okay? Now, hopefully I'll be able to show you that that's actually a fortunate way to arrange them, because these energy shells that we talked about around the atom, they have letters associated with them, and we're going to talk about in a minute. And the S shell is filled here. The P shell is filled here. 1, 2, 3, 4, 5, 6. There are only 6 electrons in that shell. In here, we fill the D shell. There should be 10 of them. And in these, we fill the F shell, SPDF. So you can stick that in the back of your mind for a little while until we actually need it. But what I'm saying is the periodic table is structured to help you understand how the atoms are built and how you can use that information to predict their behavior. Also, you got this black line here that you should be able to put in your extra credit. That is the dividing line between metals and nonmetals. So you can see most of the table is metals, and you have a few nonmetals. There are a few in here like silicon, germanium, arsenic, antimony, tellurium, that depending on their environment, the reaction environment, sometimes they behave like metals and sometimes they behave like nonmetals. So those are called metalloids. And actually, it's fortunate. Silicon is a metalloid. And our high-tech industries, computers, cell phones, so forth, they're based upon silicon, right? You have to have pure silicon. I mean, 99.99999% pure. I mean, if you ever see one of those, the pure silicon being grown, it comes out in a huge, they call them ingots, I think. It comes out in this big, huge ingot about that big around and about 10 feet long. And then they slice it. And then they do certain things to it and build the chips onto it. And then they cut them up and package them and stick them in your devices. Well, it's because silicon is a metalloid. Sometimes it behaves like a metal and sometimes it behaves like a nonmetal. And you can dope it with different elements to make it do certain things, either behave positive direction or negative direction. Okay. We talked about the information that's here. Besides the symbol is the atomic number and the atomic weight. And every periodic table will have at least that information in there. Sometimes they'll have more. That one has information on the electronic structure of the atom also built into it. Okay. Elements are arranged in the periodic table according to increasing atomic number. Okay, characteristics of a metal. Well, if it's polished, it'll be lustrous, right? If it's very finely divided, it won't be that. Most of them, when you make a real small particle size, they turn black. But if you can polish them, they will luster. They have good thermal conductivity. That's because the electrons move freely, right? So they can transfer energy from one side to the other. For the same reason, electrical conductivity is good. And they're malleable. In other words, you can bend them and mold them. There's another term that's not used here. It's called ductile. Ductile refers to malleability, but it's more in terms of stretching, like stretch them into very thin wires. Those are metals. Non-metals are just the opposite. Well, and also most metals are solid, except for, anybody done your periodic table yet? Which metal is liquid at room temperature? Mercury, right. And there's one that's really close, gallium. Gallium melts at well, put it in your hand and it'll melt. Right, so what temperature is body temperature normally in Celsius? Do you remember? Right, 98.6 Fahrenheit, but what is that in Celsius? Do you know? It's exactly 37. So the melting point for gallium is like 35 or 36. So you put it in your hand and it'll melt. Okay, but the rest of them are solids. whereas the nonmetals have a full range of solids, liquids, and gases. That's one basic difference between them. All right, it's not going to tell us. So if you have a solid nonmetal, it will probably be brittle. It won't be malleable. In other words, if you try to bend it, it'll break. But if it's a gas, of course, that's a non-starter. Or if it's a liquid, that's a non-starter. And if you look at the halogens as an example, start at the top, fluorine. Fluorine is a gas. Fluorine is a gas. Bromine is a liquid. This is all at room temperature, at 1 atmosphere pressure. Iodine is a solid. So you, in that family, you have all 3 phases represented. Okay. Oh, okay, here we've got nonmetals. And ductile is mentioned also for metals. So nonmetals have poor electrical and thermal conductivity. So that makes them insulators. They don't have luster. They can be any one of the phases, and the solid states are usually brittle and non-ductile. You can't stretch them. All right. So there's the dividing line between metals and nonmetals. Hydrogen is sort of a weird one. We don't know what to do with hydrogen. So for balance, we stick hydrogen over on the above the alkali metals. Usually when hydrogen is in a well, hydrogen can either be a +1 or a -1 charge, depending on what it's combined with. And if it's like this and something else behind it, like that, the way we write compounds, remember, you put the positive first and the negative last. It's usually a +1 in that arrangement. But if we combine it with a metal, then it's usually a -1. Okay, this often we call those metal hydrides. So hydrogen is funny that way. Okay. Now let's talk about the electronic structure of the atom. Your book refers to this principal quantum number, N. It refers to that one as the electronic shell. So when your book says shell, it means this number. We can describe each electron and its position around the nucleus with 4 numbers. These are quantum numbers. Okay, N is the principal quantum number. Principal quantum number. And it refers to primarily the energy of the electron. So all electrons that have the same principal quantum number will have very close to the same energies. They won't be exact, but they'll be very close. So this refers to energy. Okay. And the ones that are lowest energy are closer to the nucleus. That's by convention. Because if you want to promote an electron to, say, infinity, you got to add energy. So within the atom, before that, it moves from one shell to the next as you add energy. So the higher energy ones are the ones with the higher numbers. And these, the numbering system goes from 1, 2, 3, 4 on out. Whole number. Just that simple. Okay. The subshells or the L numbers, are the angular momentum quantum number. These refer to the shape of the orbital. And these are the ones that have those letters I mentioned before, S, P, D, and F. But they also have numbers. The shape can be spherical, it can be dumbbell shaped, it can be donut shaped, you have all different types of shapes. But the number that's allowed here, and think of these as subsets of the one above them. So this L number is derived from either that one, that one, that one, or that one. Right? If you have a principal quantum number of 4, then you can have a certain arrangement of L numbers. Right? It's like it branches like that. So these can have, starting with 0, 1, 2, up to n-1. So that means that if you have an n number of 4, you can have L possible numbers in that shell. All right, let's use their terminology here. This is the shell, this is the subshell. For this one, you can have 0, 1, 2, and 3. Right? Because 3 is n-1, 4 minus 1. That's as high as you can go. Okay? So you can have 4 subshells, 0, 1, 2, and 3. 3, you can only have 0, 1, and 2. Right? 2, you can only have 0, 1. And 1, you can only have 0. Okay? Okay. I see some smiling faces, some grimaces, and some like, oh God, what did I get myself into? And these, this one is, and we're given these letters because if we try to use numbers when we start to draw the electronic configuration, all those numbers would get confusing. So we keep these numbers, and then these we give letters. This one's S, P, D, and let me put 3 in here, F. And that's all you need. We don't have elements that can go any higher, right? Because remember the lanthanides and actinides, they're filling F shells. Right? That's as high as you can go. I mean, theoretically, you can go to G's and H's, but I guess you could promote electrons into those orbitals if you want. But we're not going to do it. So that's NL. I need 2 more, right? All right. Angular momentum quantum number, the magnetic quantum number. This one is M sub L. The magnetic quantum number. This one refers to orientation. Which direction is it pointing in 3-dimensional space? And these are based upon these numbers. So you take these numbers, and then you can construct how many of these you can have at each one of these levels, which in turn were constructed from each of these levels. So it compounds. So the orientation, these numbers are based upon those L's, and it can be 0 in the middle, and you can have, let's see, you can have minus L to plus L in unit steps. So if your L starts at, say, 3, if it starts at 3, you can go to 2, 1, 0, it's negative, plus 1, plus 2, plus 3. See what I mean? Take the L is the extreme ends, negative and positive. And then you have unit changes in between. Go there. So you have 1, 2, 3, 4, 5, 6, 7 possible F subshells in the magnetic quantum number. Okay, and the last one is M sub S, I believe. It's not showing it. There it is, M sub S. This one's the simplest one of all. This is the spin quantum number. And the spin quantum number can either be, and it's theoretically, which way is the electron spinning? Is it clockwise or counterclockwise? So it can either be plus 1/2 or minus 1/2. That's it. So each one of these could have a plus 1/2, minus 1/2, plus 1/2, minus 1. It can have, and there's only one electron that can occupy those. So each one of these can have 2 electrons. Plus 1/2, minus 1/2, plus 1/2, minus 1/2. So for this particular level, this F level, you can have 2, 4, 6, 8, 10, 12, 14 electrons. And as you add the electrons, if you add a proton to go with them, you get a new element. So that's why we have 14 elements here. 14 elements, 14 electrons, 14 protons, and their electrons make 14 in the lambda, and 14 in the actinides. Because you're filling 1 electron, 2 electrons, and you go to the next 1, 2, 1, 2, 1, 2, or plus half, minus 1/2, plus half, minus 1/2. Oh, that's why you have 14 there. If we go to D, right, D, that would only be minus 2, minus 1, 0, plus 1, plus 2. So that'd be 2, 4, 6, 8, 10. That's 10 protons or 10 electrons. So in here, we're filling those D orbitals. So you should have 10 of them here. So now it makes sense why you have so many in that region. And for these, you have P, or L equals 1. Now it's minus 1, 0, plus 1. That's 2, 4, 6. 1, 2, 3, 4, 5, 6. And then if we go back up to 0, that's S. They can only have 2. They can only have one level of the magnetic quantum number and 2 electrons. 1, 2. There you go. That's why the periodic table is structured that way, based upon this arrangement of electrons. Okay. These are just pictures here. Let's see. Maximum number of electrons. Okay. It's the discussion I just gave you. You can have a maximum of 2 in the S, 6 in the P, 10 in the D, and 14 in the F. And that corresponds to elements that you're constructing in those regions in the periodic table. Let's see. They can have some weird shapes. The S orbitals are the easiest to understand. They're spherical. The P orbitals are kind of dumbbell shaped. The D orbitals are like a double dumbbell, and the F orbitals are really weird. Now, I don't want you to think that we've actually seen those. Nobody has seen those orbitals. These are mathematical constructions and visualizations of what we think that space looks like. And when those electrons are in that space, they're not in a location, right? You can think of them as they're waves spread out over that region of space. But sometimes the shape of the orbital helps us understand how reactions can occur. Why 2 elements approaching from this direction don't react. But when they approach from a different direction, because the orbital orientation is such that then you can get overlap of the orbital, now you get a reaction. Right? So that's one way that the shape can help us understand a reaction. Orientation, let me make a point of that one. Orientation here. So if you have the p orbital, where you can have a -1, 0, +1, look at it, three-dimensional space. Right? So X, Y, and Z. So the Z is going back into the board. Okay? So you can have a 0 orbital like that. You can have a -1 orbital like that, and a +1 orbital like that. Right? Orientation in space. 3 dimensions. That's the easiest one to understand. Supposed to go till 11, I think. Am I halfway through yet? Okay. All right. Shells, subshells, and orbitals. So these are shells, these are subshells, these are orbitals. I'm trying to relate these to what your book calls them. And I think your book talks about these things. But now what we want to do is use this information to construct an electronic configuration around an atom. What do we need to know? We need to know how many protons, consequently how many electrons are out there. So once you know how many electrons are out there, you can start filling them in order. Right? And these are the rules that you use. I'll just breeze through these and it'll make more sense when we actually go to make one. The Aufbau principle. When all this stuff was being developed, the Germans were on top of the world. Right? So they got to name stuff. So Aufbau, I don't have the slightest idea what that means. I just think of it in these terms. Aufbau means do it this way. Okay. In order of increasing energy. So the electrons go in as you're building your electronic structure. The electrons go in the lowest possible energy level first, and then you start stacking them with higher energy levels because the lower ones are occupied. Hund's rule. These orbitals and subshells are occupied by electrons that they have to have at least one electron in them before the second electron can be added. In other words, let's see. Okay, let's use the P as an example, right? Because it's simpler, right? It has the -1, 0, and +1. So you can think of these as, we can draw this line, this line, this line. So we can put electrons in there, and they can have half, +1/2, -1/2, and we represent these with spin up, spin down. Okay, just to separate them, right? So Hund's rule says that when you're adding electrons in one at a time, when you get to one where you have multiple magnetic quantum number levels like this, you've got to have at least one electron in each one of these before you can go back and start adding the others. So if you have 1, 2 electrons that are supposed to go in there, you're done. You don't put them next to each other. If you have another one, say you're going to the next level, the next element up, and you got another electron, you go to the next one beyond, now you can start putting them in like that. That's Hund's rule. The Pauli exclusion principle is that it just says that each electron has a unique set of quantum numbers, these 4 quantum numbers. And each electron has that set of numbers, and no other electron can have that exact same set. They could have this number, that number, that number, but if they do, they have to have opposite spins. Okay, that's the Pauli exclusion principle. Now, I better leave that up there in case I want to use it again. Okay. So remember Niels Bohr. He was able to predict energy levels for the hydrogen atom because it only had 1 proton and 1 electron. Very simple. If we go beyond that and we start adding more protons and more electrons, you get interactions. Right? You get a buildup of positive charge in the nucleus, which tends to draw electrons closer. And you get all these electrons out here that have the same charge, and they tend to repel one another. So they modify the energy levels that are available because of that. And it's all mathematical. So what we need to do is learn the practical approach to building the electronic structure of an atom. Right? And this is one way that chart, what it shows is here is the s orbital can only have one. Right? So it's 2 electrons in it. That's why the first 2, you only have 2 columns filling the s orbital. And then the p's are up here. But when you get to the shell number 2, you can have an s and a p. Right? Because shell number 2 says you can have 0 and 1. Right? It's n minus 1 is the highest, so it's 0 and 1. So you can have an s and a p for the 2. Well, we're okay for now, but once you start adding enough protons to get the extra electrons that you want to put in higher orbitals, now you get the level 3, the principal number 3. Now you get s, p, and d possibilities. And their energy spread out a little bit. But once you get to 4, the interactions are such that 4s is lower energy than 3d. Okay, so it starts to get really complicated. So we need a method that will help us insert electrons in the proper energy level as we build successively larger atoms. Okay, that's the whole point of that one. The next one, this one, is a method that is almost foolproof for filling orbitals. Okay, there's a lot of information there that may not make sense. So let me erase some of this. And we use a shorthand for the electronic structure of atoms. The first number is the principal quantum number. Yeah, if you need to get up and walk around, that's fine. If you need to go to the restroom, go ahead. It's being recorded, I hope. So you put the number first, like that, 1. Or if it's if you're in the n equals 2, then it would be 2. Or if it's 3, you put 3. Okay. Then the next level is going to be the L numbers, or the S, P, D, or F. So you can go like this, right? So can we go any higher than that one? No, because you can only have n minus 1, right? So you have S, that's it, for the first quantum number. For the second quantum number, you could have, let me put them a little closer together. You could have S, but you could also have a P, right? Because this is 2, that represents 0, and that represents 1, n minus 1. If we go to 3, then you can have an S, you can have a P, and you can have a D, because this represents 0, 1, and 2, n minus 1. Okay? That's the shorthand. And at this point, how many electrons can we put in there? Well, for the S's, we can only have 2, maximum of 2. So we put, if we have both electrons in there with spin up, spin down, that's as far as you can go with the S's. So all of these S's will only have 2, maximum. The P's can have how many? -1, 0, +1, 2, 4, 6. They can have a maximum of 6. Okay? And all you have to do is look at the periodic table. You know where the P's are being filled on the right-hand side. How many elements are in a period there? 6. So that tells you P is 6. If you go to the transition metals, how many are in there from left to right? 10, right? 10. -2, -1, 0, +1, +2. 2, 4, 6, 8, 10. So the D's can have a maximum of 10. And then if we get up to F's, we have to go to 4 to get to F's. You would have 14 possible. Now, is that the correct order, energy order from left to right? Low, next, 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 higher energy as we go. Well, what we need is this arrangement. We write the 1s's down here. All right, 1s, 2s, 3s, 4s. Let me see how far it goes. Down to 7. 5, 6, 7. S, S, S. Then we put the P's. We can't put a P up here because 1 can't have a P. It can only have a 0. So this one has a 2P. 3, 4, 5, 6. Probably 6 is enough. P's. And if we write them like this, now we can't have a D over here. We have to go to 3 for D's. But 4 can have a D. 5 can have a D. And that's probably enough. We can't have any F's out here, so we have 4F, and we have 5F. We could do D's and F's down here, but the way we're going to fill, then we don't need them, right? So when you're starting to fill, and what I mean by filling orbitals is you're going from one element to the next. So you're adding an electron each time. So the order of filling goes diagonal. So you go here, go there, there. All right, so you go 1s, 2s, 2p, 3s. Then you go 3p, 4s. Go to 4s before you go to 3d. So you go like that, like that, like that, that. So that's the order of filling. And this allows you to take into account those shifts in energy levels that occur as we get bigger and bigger atoms. They start interacting and changing the energy levels, and they get out of order. Okay? Now, that's a foolproof way to do it. But there's an easier way, using the periodic table. Okay? Let's see. Okay, we're going to do nitrogen. Condensed notation. All right. So let me erase this one. We'll do nitrogen. So what do you need to know? Nitrogen has how many protons? 7, right? Nitrogen has 7 protons, which means for the neutral atom, we got to put in 7 electrons. Right? So we do them in order. 1s, 2s, 2p, and 3s, and 3p. We may not need all those, but they're there in case we do. So how many can go in here? 2, right? Okay, we got 5 more to go. How many can go in here? 2. So we got 3 more to go, right? So all those 3 can go in here, right? And we're done. Right, so we don't need the rest of them. So that would be the electronic configuration for nitrogen. Now, if we need to understand some of the characteristics of nitrogen that are unique to nitrogen, we need to know something about how they're arranged in the orbitals, right, down at this level. This is just the subshell level. The orbital level will be like this, right? P, -1, 0, +1. And how would they go in? They go like that, and like that. Okay, this helps us understand a characteristic of nitrogen that can be measured. It's called diamagnetism. These are unpaired electrons. They're all spinning in the same direction, which means they generate and respond to magnetic fields. If they were paired, they would cancel out. And if we had all three of them filled, they wouldn't respond to a magnetic field, a strong external magnetic field. So this information is useful if you need to know it. If you don't need it, if you just ask, all right, write the electronic configuration, just do that. Okay. There it is. Well, in that bottom part of the slide, they're throwing it in there like that. We're just saying that this is S, so it's up like that, and this is like that. I prefer that way to the boxes. It's harder to draw those boxes, easier to draw the lines and do the half head arrows. How about sulfur? Let's see if we can do sulfur. It's got more protons, doesn't it? What group is sulfur in? It's a calcagen in the oxygen group. Sulfur, how many protons does it have? 16. Okay, so we go 1s, 2s, 2p, 3s, 3d. Oops, sorry. 3s, 3p, excuse me, 4s, and 3d. If we need them, maybe we don't. Okay, so we're building low energy to high energy, Hund's rule. No, Aufbau principle, excuse me. So we put 2 here, right? We can put 2 there, maximum. We can put 6 there. So we got 10 so far, right? Okay, we got 6 left over. There's 2, 6. So we don't need this one, and we don't need that one. So that's sulfur. Okay. Now I'm going to show you something. Okay, there's sulfur. Unless, if you're asked to give the complete electronic configuration of an atom, that's what you do. But if you're allowed to use shorthand, I mean, this is shorthand, but a shorthand, then what do? You can go backwards on the periodic table from sulfur. Backwards this way, and then wrap around and start at neon. Neon is complete. Noble gases are complete. In other words, if we went further, like sulfur, chlorine, argon, if we went to 18, then we would fill this one up completely. And every orbital in there would be full. That's a noble gas. That's why they don't play with others. They're perfectly happy right there. They've got all their orbitals filled. You know, outsiders not invited. So what we can do is go backwards and say, let's start at neon because it's full, right? And it has 10, right? 10 electrons. What goes beyond that one? Well, here's full, P is full. That's 2, 4, 10. That's neon. Now we can go the rest of the way. 3s2, 3p4. That's also sulfur. Okay. If all you need to know is what do the outer orbitals have in them, this is perfect. Okay. So, and the reason I introduced that topic right now is because look what the next one is. Barium. Where's barium? It's in the second family, way down toward the bottom. It's 56 electrons. Right? If you had to draw all of those out, it would take you forever. 56. So let's use the shorthand. Take barium and go backwards. Barium, cesium, wrap around xenon. Xenon 54. All of those orbitals are filled, completely full. But where do you go from there? This is where the structure of the periodic table helps out a lot. So we got xenon. Now, we're at barium. Where's barium? It's in the 6th period. For the s orbitals, that's 6s. And there are 2 electrons, right? 1, 2. So all we have to do now is write 6s, 2. There's 2 plus 54 is 56. Okay? So knowing the structure of the periodic table will help. I mean, we could do barium all the way. We just need to know that when we pass through the first 2, we're filling s orbitals, 3 s's. Then we're going to jump over to aluminum, say, and that's 3 p's. Go all the way over, and then 4 s's for potassium, calcium. But when you get to the transition metals, notice what happens. Instead of going, you fill the 4 s's, right? You're on the 4th period, but now you're getting into you're not going to the 4 p's. You got to cross over the d's. So when you use the periodic table to help you do this, you got to go here and then here. So in the 4th period, the d's are filling 3 d's. So 4s, 3 d's. Then you're back to 4 p's. And then you go to 5 s's, 4 d's. So it's doing the same thing here as in that diagonal chart. It's just that if you use the periodic table, you don't have to write that chart. Now, what happens when you get down to here? Right in here. You go 6s, and this is 5d. Then you go down here to 4f. Back up another one, from 5 to 4. Now, is that what happens over here? Let's see, if we were 6s, 6s, then we go back up here. Well, actually, now down that high, it starts to get squirrely. So I'm not going to throw any of those at you, okay? And there are other reasons that some elements deviate from this procedure. You would expect them to be a certain electronic configuration, but you go back to the energy Aufbau principle, and it deviates from this slightly. Okay, maybe I can point those out later, but if I don't, if there's no slide on them, then don't worry about it. I won't throw those at you anyway. Okay, there's the full, and there's the abbreviated shorthand notation. Let's see. I'm going to have to skip that one. There it is. That's sodium. And notice which one is being filled at sodium? The s orbital, 3s1. Look at sodium. It's in the first column. It's the first one. It's got only one s electron. So that's why when sodium forms an ion, it forms a +1 ion because it gets rid of that one electron. If it gets rid of that one electron, what does it look like then? It looks like neon, right? And you can think of it in those terms. When a metal or a non-metal gains or loses electrons respectively, they're trying to look like noble gases. They're trying to do whatever they can to end up with filled orbitals, right? Whether that's losing an electron or gaining an electron, whichever is easier, right? It's easier for sodium to lose an electron than it is to gain enough to go all the way over to argon, isn't it? Right? So it just loses an electron, looks like neon. But if you're way over on the other side, chlorine, it's better for chlorine rather than go all the way back to neon to just gain an electron. Now it looks like argon. Right? So that's why the halogens are -1 charge when they're ionic, and the alkali metals are +1 charge. And the alkaline earths are +2 charge because they just lose 2 electrons, which means 2 negatives are gone, excess of 2 positives. Those are your ions. and they look like the noble gas that's just above them. Okay, now things should be starting to make sense why those charges are what they are. You don't just memorize the charges anymore, they make sense. Okay, so what you'll also notice is that for each of the families, the outermost electronic configurations are similar. In other words, for say lithium, sodium, potassium, rubidium, cesium, all of those, there's an s orbital on the highest energy level that only has one electron in it. Okay, they're at different energy levels. That's why they're not exactly the same in their chemical reactivity. But because that one electron, all they have to do is lose it, and it makes that one positive charge, they behave similarly. That's why that Mendeleev didn't know it at the time, but that's why those elements fit in that family. Okay. And that's where the Roman numeral arrangement, the numbering comes in. This periodic table has both systems. It's got the new system 1 through 18, and it's got the Roman numerals. The Roman numerals with a suffix of A are the representative elements, right? The first two columns and the last six are all A's because they fit in that octet rule, right? 2 in the s orbital, 6 in the p, 2 plus 6 is 8. And that works pretty good for the second and the third periods because you don't have the transition metals in between to mess things up. So it works really well for the second and third periods. Of course, the hydrogen and helium are off by themselves. If there's anything that they obey, it's the Duet Rule. So the Roman numeral tells you how many electrons are in that outermost shell. If we're in the boron group, it's 3A. There are 3 electrons in the outermost shell, which means if they're going to acquire the noble gas configuration, they're going to lose 3 electrons, become a positive 3 charge. Let's see. Fluorine and its group has a 7A. So they have 7 electrons in their shell and they only need 1 more. So that tells you that they have 7 electrons in what we call the valence shell. Right, so we're harking back to the earlier concept of valence, and now we know what the valence means. It's how many electrons are in the outermost shell. And the outermost shell is the one that determines the chemistry. The others, all those electrons underneath, like in this case, for lithium would be the 1s or the 1s, 2s, 2p. For sodium, 1s, 2s, 2p, 3s, and 3p. Those are known as core electrons. They don't react. They're not they don't get involved in reactivity. Just the valence ones, the outermost shells, the ones that are not complete. The ones that are beyond the noble gas configuration. Those are the valence electrons. So that's why the Roman numeral system was useful, because if you knew the Roman numeral 3, there were 3 electrons in the valence shell. Or if you knew for oxygen, if you knew Roman numeral 6, oxygen has 6 electrons in its valence shell. So if it gains 2 electrons, now it has 8. So that's why oxygen and everybody in its group prefers a -2 charge, because you add 2 electrons. I haven't heard any questions. Are you just numb? That's understandable. First exposure. All right, so this is talking about filling the S area, the D area, and the P area. And let's see. Okay, they're not going to show F area, but it's It's real. The lanthanides and the actinides, you're filling the Fs. I'm not sure what they're getting at with the distinguishing electron. It's just the last electron you add when you're building your configuration. Okay, I see what they're getting at. It's got one more electron than the one before it. That's, big deal. I guess the authors needed to fill in 2 or 3 pages, so they invented something. Okay, so the columns, these groups, are their chemical characteristic, their properties are determined in that group by the number of outer shell, the valence electrons. That's what determines their reactivity. Okay, classification of the elements. We need to get into that. Well, we mentioned, I did mention the noble gases, right, and the other names of some groups, the transition elements, and those lanthanides and actinides are called inner transition elements. I guess because they're inside the transition region. All right. So there's another representation of the periodic table. Elements in group 1 and 2 are referred as what? What orbitals are being filled in groups 1 and 2? S, yes, because they can only have 2 electrons. Oh, we're in concept questions, so we're about to end. Let's see, consider 2 elements. One is a gas and the other is a solid. All right, so let's try to make sense of this thing. All right, you got 2 elements. Let's see, I can't use Y because that's yttrium. What's another one that's not being used? T. There are bunches of T's with little letters, but there's not one with just a T. Okay, so we got one that's a gas, right? What's the other one? Solid. Okay. Each contain identical number of electrons in their outer shell. Same number of electrons. Number of electrons here equals the number of electrons here. In their outer shells. So these are valence electrons. All right. Oh, so we got to choose. We're looking at the choices here, A through D. So we're given a multiple choice test. Okay, so let's process of elimination, right? These elements are fill in the blank 1 and 2, and then they contain so many neutrons, respectively. Well, let's say which one of those matches gas and solid. Fluorine and iodine? Yeah, fluorine's a gas, iodine's a solid. So that could be fluorine and iodine. That's possible. How about nitrogen and sulfur? Yeah, nitrogen and sulfur. That's a gas. That's a solid. All right. Oxygen and sulfur, that works too. Okay, so it looks like we're not going to be able to eliminate. So the last one's fluorine and iodine. Okay, so let's go to contains how many neutrons respectively. All right. That's a little tricky because they don't tell us what the isotope is. So we sort of have to make an assumption. Let's say the most common for fluorine would be 9 and 9 and 19. 18.9999. So the more common isotope is probably 19. Okay. How about iodine? 53 and 127 is probably the most common. Now, why did I say that? Because the average value is almost 127. Right? So it has one isotope that's a little lighter, but it's not very common. Right? So it drags the average down a little bit. Okay. Is that wasted on anybody? How about, let's see, nitrogen and sulfur. Nitrogen 7, and it's probably 14 is the most common, isn't it? 7 and 14. And sulfur is 16, and what's the most common, you think? 32. And let's see, oxygen is 8, probably 16, isn't it? And sulfur then is 16 and 32. Okay, so how many neutrons do we have here? 10. How about this one? 74. Is that right? How about this one? 7 neutrons. This one is 16 neutrons, right? And this one should be 8 neutrons. And this one would be 16 neutrons again. Okay, now which one does that match? 10 and 74? Yeah, the first one hit it. Because 14, nope, that's not right. 14, nope. 16 for oxygen, nope. 19 for, what they're doing in B, C, and D is giving you the mass number, not the number of neutrons. The only one that's got the right number of neutrons is A, correct? So we just solved the type of problem you might see on an exam. Graphing techniques. Why in the world do we need to draw graphs? Because your math teacher says so, right? Did everybody draw graphs in math class? Good. So this may not take as long as I thought. You remember the characteristics of a Cartesian system? I'm using big words again. Remember this. That's the beginnings of your Cartesian system. What sheets? Graphing technique? Oh, one of those? They're up here. You can get them at any time. No, you mean the method? Those are extras. There are 4 of them in the method itself. And these are extras in case you mess one up and you start over again. Okay? So the Cartesian system divides 2-dimensional space into, starting from a central point, right? That's the origin. I bet the camera. Oh yeah, I did pick it up. Okay, so this is what we normally call the x-axis, right? This is the abscissa. How do you spell that? Like that? Yeah. This is the y-axis. What's it called? Yeah, ordinate. Okay. And the 2-dimensional space is divided into 4 quadrants. Okay. So everything to the right of the origin on the x-axis is positive. Everything to the left is negative. Everything above on the y-axis is positive, and everything below on the y-axis is negative. So your values if you plot a data point anywhere in this region, you know that if it's going in here, both the X and the Y will be positive. So what does that data point mean? Well, it means you go over this many units positive X and this many units up positive Y, and that's your data point. Right? So, and you may have, if you drew these in math class, you may have been required to put the values in here. X1 and Y1, whatever that has to be. And that tells you where it is on the graph. If you had a negative X, it'd be like negative X over here, but in positive Y, or negative X and negative Y, or positive X and negative Y. Okay. Most of the graphing that we do in the sciences, not all, but most, is going to be focused on that quadrant. Because in reality, you rarely have negative values. Okay. So another characteristic that's unique to the sciences that they may not have described in math class is when you actually run the experiment, what does that represent? In the real world, that represents a measurement. You're making a measurement of some physical phenomenon. Okay, so naturally, if you make the measurement several times, the same type of measurement, you expect to get the same results, you won't. You might get one here or here or here or here, like that. There'll be a little bit of a spread there. That's called experimental error. And every measurement has error. So you put that point there, but that may not be reality. Okay, that's the whole point. No, that wasn't meant to be a pun. Oh, another thing is this measurement, when we're using this system, the measurement is based upon something that you set up as an experiment. And as the experimenter, you decide the input of one value. And then the experiment gives you the result, which is the output of another variable. Okay. So by convention, the X variable is the independent. That's the one that the experimenter chooses. Like if we were going to measure pressure and volume of a confined gas. If I say, I'm going to pressurize this gas to 3 atmospheres, we put enough pressure on it, what's the volume? The volume would be here. This would be pressure, this would be volume. So this is the dependent variable. Right? That's what the experiment tells me in response to my independent variable. The experimenter determines what this is, the experiment spits out the dependent variable. And then when you plot those two numbers together, they correlate, right? They're bound together in the experimental measurement. They correlate to some point here. Okay? And you can do that with, in our example here, change the pressure, different pressures, you get different values of volume, right? And you plot them on your graph. Okay, why bother? I mean, why put them on a graph? Why don't you just put a list of numbers, right? I did the pressure here, I get the volume here, there's your numbers, right? The human brain isn't designed to interpret lists of numbers. It just doesn't work very well. We're visual creatures. So if you can put your data, your measurements in a visual format, this is one of many, then it's easier to wrap your brain around it. It's easier to see trends, to interpret the data. I don't know how many scientists I've known in my career who, I call them shotgun experimenters. And from my experience, the field experiments where you have crops and you put treatments on them and you see what their response is, right? Rather than design the experiment, they just go out there and shotgun their treatments on the field, and then they go back later and see what the effect is. That's not experimentation. I don't know where I was going with that. Visual representation. Okay, and there are many things that you can do with your data once you get it in this format. Well, lists of numbers, you can use statistics on them, right? Has anybody been introduced to statistics like means, standard deviation, that type of stuff? You can do that with just bare numbers, but they also carry an added significance and a better understood meaning if those statistics go along with a visual representation. So, for example, let me clear some space here. Let's say we make, we set the independent variable, and the dependent variable gives us values that go like this. Right? We're increasing some magnitude here on this one, and the dependent responds with an increasing magnitude on that axis. Right? Anybody see a trend there? It's like a straight line, doesn't it? Okay, that's good. Scientists love straight lines because they're so well behaved. So if you connect the dots, or remember what I said about experimental error, that's probably not going to be the way they do. You're probably going to have maybe one over here and one over there and one over here and one over here. And what you try to do, if you think it's a straight line, you try to best fit. So manually speaking, you would get a ruler and you would minimize the distance between the line you want to draw and these varying dots. So the best way to do that is use a transparent ruler, right? Because if you lay it up here like that, it's going to cover up some of your dots so you know where they are. So a transparent ruler would make it easier for you to best fit your straight line. So let's say our straight line actually does that. There we go. Okay. So that's what we're doing is minimizing the variation, minimizing the distance from the line of each one of these. And in statistical terms, that's called regression analysis. So now that we've got a straight line, what can we say about the straight line? We can write a formula for that, can't we? Anybody remember this one? Right? Y equals mx plus b. So this is the y variable, that's the x variable. This is what? The slope. And this is? It's not a trick question. It's the y-intercept. If we extend this line down here, that's where it intersects the y-axis. See, I had a thought and it just completely evaporated. Let me see if I can refresh my memory here. Say we make measurements from here to here, right? We can draw a line with fair confidence, minimizing the variations from this point to that point. But suppose we want to know, all right, what if, after I get the data, what if I graph it and I say, I didn't make a measurement in this position right here, right there, right there, right? But I'm curious, what if I had made a measurement there? What would the y value be? So I just go up here and across there. That's what the y value would be. That's how you read it off the graph. That's called interpolation. That's the safest way to use a graph. Stay within the measured points. You have less variability there. But sometimes we're interested in what if outside that range, right? Go down here, go all the way down there, or we go up here like this. Anything in those regions is extrapolation. There you're in no man's land, right? Because you don't know what the curve's going to do after that. It could go like that. It could go like that. It could go bang like that. So there's a lot more hazard possible in extrapolation than there is in interpolation. Okay. So once you have that formula, well, I would add this. The points don't have to be straight line. Very often they're not. Sometimes they're in some type of a curve. But you can still fit a best fit line to those points. What you want to do is, if you're good freehand, then you can like draw pretty close and minimize the variation. If you're not good freehand, there's this thing called a French curve. It's a device. It's kind of like a straight edge, only it's curved. And I think it generally goes like, let's see, like this, maybe like that, something like that. Maybe this is smoother like there. And what it gives you is a variable radius curve, so that you can move that curve around so that it more approximates the curve that you've got. It's varying radius. So if the curve is really tight, you would use this part of the French curve. If it's really spread out, you would use this part, and it would help you draw a best fit curve to your points. Let's see. Oh, okay. So back to our straight line. How do you get the slope of the line? What does the slope mean in relationship to that line? No idea? I'm sorry? Well, yeah, I mean, it's more than that. Rise over run, there you go. All right, so M equals what we call rise over run, which in interpreting for our graph is a change in Y divided by a change in X. Okay. So on the graph, it would look like this. This is a change in Y. This is a change in X. So you need, what's the distance here? Right there. That's your change in Y, and this is your change in X here. Okay. And then you ratio them, that gives you your slope of the line. Now, if you've drawn your curve, or you've drawn your best fit line, and there are 2 points on that line that fall exactly on the line, that's good. Because now you can use those values to calculate this value. Because remember we had, say this point, say it's a real point here, a real point there. This is going to be x2, y2. This is going to be x1, y1. Right? So you say y2 minus y1 is here. X2 minus X1 is there. Okay? So you can draw that straight out of your data set. What if you draw the line and there are no measured points from your data set on that best fit line? Well, then you have to interpret. You have to say, okay, I'm going to pick 2 points. Preferably the farther away they are from each other, the better. So you maybe take a point, pick a point here and a point here, and say, all right, what's the Y value here? What's the Y value here? Subtract this one from that one, goes in there. And take the X value here, subtract the X value there, it goes in there, calculate your slope. Okay? Am I putting anybody to sleep yet? That's long past. Okay, now that you have the slope, and these are variables, y and x are variables, so you don't have to put any numbers for them. Not yet. Once you've got that slope, and this is just for straight lines. Once you've got the slope, how do you find the y-intercept? The easiest way is, especially if you have a line that passes through a real data point that you measured, is to take that data point, put the y value in here, the x value in here, the slope there, solve for your one unknown. Okay. And again, if you don't have a measured data point that falls exactly on your line, pick a point. Pick a point on here, find out what the y is, what the x is, put them in along with your slope, solve for your y-intercept. Then you take the real value. Let's just make something up. Say your slope is 2 plus, and your y-intercept is 1. There you go. That's how you would report it. Once you determine what this is and that is, you write it that way. Now, if this y is something like volume, then you would say volume. And if x is pressure, then you would put pressure. So that's how you would report it. Okay. And usually, at least in referee journal publications, when you submit a graph like that, you usually do, once you've decided on what you think is the best fit curve, you, on the graph, you put that, this interpretation on the graph to show what that straight line is mathematically. You put a bunch of other stuff on there too, but I don't want to bore you too much. Okay. Besides, it won't make any sense to you until you take statistics anyway. Anybody going to take statistics? No? Yeah. Oh, good. Good. Okay. It's fun. I like statistics because it has rules. Okay. Let's see. I'm trying to follow along here. Yep. There we go. There we go. Nonlinear relationships. Okay. All right. So let me make some room here. How are we doing on time? 3/4 of an hour left. Eventually I'm going to get to the best way to use your graph paper, right? You've got limited space in that graph, or that piece of graph paper, and you want to use all of that space that you can. Because if you spread your graph out, it's easier to interpolate. Right? You can read finer detail if you efficiently use the space that's available. Okay, so let's suppose our data is not linear. And pressure volume is a perfect example of that. Oh, by the way, let me just put this one over here. That right there, that is a direct relationship. What that means is as x increases, y increases. So x is here, y is there. Okay. X is here, y gets bigger. That's a direct relationship. I think that's what they call it. There are various ways to interpret. Well, no. Direct relationship, direct proportion. Direct proportion. Which means positive slope, right? A positive change in y for a positive change in x is slope. So what would be an inverse relationship? Negative slope, right? Negative slope. So if our relationship went this way, it would be an inverse relationship. And the slope here, this slope is positive, this slope is negative. Right? So y is decreasing as x increases. So the change in y is negative, which makes the slope negative. Okay. Nonlinear relationships. Okay, and this is one that you're going to be graphing yourself, and I'm working off figure 3 on page 19. Okay, so let's say we're only going to use the positive quadrant. So there's our starting point. What's going to be on this axis? What's going to be on that axis? Based on the data and the experiment that I described earlier, as we increase the pressure on our gas, what happens to the gas? The volume decreases. So as the pressure goes up, the volume decreases. We're changing the pressure on that axis. And the response is the dependent variable. So if I put these points in here, we find that at low pressure, we got this much volume. And then as we increase the pressure, the volume decreases. Something like that. Right? So a best fit curve here would not be a straight line. Right? It would be more like that. Okay? In mathematical terms, that's a hyperbola. Remember what a hyperbola does or doesn't do? A hyperbola never touches the axis. It can go out infinity and never touch that axis. Same this direction. That's a hyperbola. Well, actually, it's more. Right. You can. Well, in our case here, we can express this equation as pressure times volume equals a constant. Okay. That's Boyle's law. We'll get to that when we talk about gases. But notice that if this is constant, then if this goes up, that has to go down. Or if this goes down, that has to go up. In order to be constant, it has to do that. That's an inverse relationship. Okay. So as pressure goes up, volume goes down. But it's not a straight line. That's a straight line relationship, but this is not. So what do we do? How do we describe that? Well, this describes it. But is there a slope on that line? Actually, there are infinite number of slopes on that line. It depends on where you measure it. If you measure the slope here, it's the same as the tangent to that line of this straight line. That's the slope on that line. But if you measure it over here, right, slope changes. So it's constantly varying slope on that curve. So for our purposes, you don't have to report a slope for that. We don't ask you to do that. But there's something interesting. Scientists, when they can, will manipulate their data. And if possible, create a straight line out of it. And we can do that out of this data. And that's what they're showing you. The top part of this frame is the curve, and the bottom part is the straight line based upon the original data. Okay? So if we say we changed the pressure, and we got volume measurements. So each measurement, that's a data point. Right? X, Y, X, Y, X, Y, X, Y, or PV, PV, PV. But that gives us a curve. What if, mathematically speaking, why don't we divide both sides of that curve by V? I mean, that equation. Right, we can do that, can't we? Algebra says if you do the same thing to both sides of the equation, you haven't changed it. So if we take this one and divide both sides by V, believe it or not, I'm giving you a bunch of answers to the questions. You're paying attention. Divides both sides by V. Right, we can do that. Now, what is that? This one goes away, right? Okay. And the V's on this side now. But I'm going to pull that constant out. Right, can I do that? Like that? Okay. Actually, it'd be, from my argument set. Huh? Well, what does this represent? It's the same as K times 1 over V, isn't it? K divided by V is K times 1 over V? Yeah. Okay. I want to put the K here. And I'll show you why in just a minute. Okay. Now that we've got this part of it and this part of it, what does that look like? Y equals mx. We got a straight line. What's B? In this case, B is equal to 0. Our straight line goes through the origin. So if we take the data here, pressure volume, and we transform the volume into its reciprocal and plot the pressure against the reciprocal, we'll get a straight line, and it'll go like this. Okay? So now the inverse relationship of PV is now a direct relationship of P 1 over V. And this would have to be 1 over V for that plot. Okay? That's what's being done here, and that's what's asked of you in some of these exercises in the back. Okay. So, when you draw these graphs, keep this one thing in mind. A graph stands alone. It stands on its own two legs. You need everything in that graph for your reader to interpret. Right? So you need maximum information in there. Right? So what do we need? And this is what you should have on your hand-drawn graphs. I'll just leave that. Right? You're going to put your data points, and you can put a best fit line, right? Whether it's this one or that one or whatever else it is. You're going to label your axis. So rather than put it out here, we usually put it here and here. And then you want the units of measure that are involved. Right? In this case, it's probably atmospheres. I'm not sure if it is. In this example, it's atmospheres. Yeah, atmospheres is measure of pressure. And volume is what? In this case, it's they put liters. But it could be something else. You want to label the axis and units of measure, or you can put them in parentheses. That's valid too. You want a title. What is this? Right? What was your experiment? Maybe something like this. Response in volume of gas to change in pressure. Something like that. That tells you what you're trying to present here in the graph. Okay? So what else is missing? We don't have any tick marks. We don't have a grid here. So you need, in graphing programs, they usually call them tick marks, major ticks and minor ticks. So these would be your major ticks, and you only have to label the major ticks. And, yeah, what value is this? Let's say this is I don't know, 1, 2, 3, 4 atmospheres. And then between it are going to be subdivisions. Right? Could be, in this paper, you've got major, you've got dark lines and then light lines in between them in the grid pattern. The light ones, I think there are 5 of them between the majors. That's kind of awkward, right? Especially if you're in the decimal system. So if we have 1 here, you want maybe 10 subdivisions, so you can go tenths, 1.1, 1.2, 1.3. It's easier to read that way. So how would you do that in that paper? Well, you take in 2 dark lines, and you go 2 dark lines, that would be 1 major tick mark. And then between those 2 would be the 10 minor tick marks, would be your tenths. It's easier to read, right? Okay, so you need to label your major tick marks, and same for here, right? And each one of these would be like liters, or you maybe a tenth of a liter. You could go maybe here would be 0.1, and if you had 10 marks from 0 to 0.1, what would each one of those minor tick marks represent? The next decimal over, hundredths. Right? So each tick mark would be 0.10 here, 0.01, 0.02, 0.03. Okay, follow me? Okay. So now we got major labels, we got tick marks labeled, we got our points plotted. Of course, you're going to do this before you put your points in because you don't know where they go until you know what the measurements are. And then you do the best fit curve, you put a title up here. And sometimes you have subscript comments down here to help your reader understand what's going on. We won't need those for this one. Huh? A scale. Oh, like a scale in here somewhere? No. No, because you're taking care of that with this. Okay. Okay, now, I skipped over some important points. I alluded to it with graph paper. You got graph paper that's like 8.5 by 11, but of course the graph only is part of that paper. So the next, actually the first question is, how do you want to orient your graph? Do you want it to be this way? Or do you want it to be this way? How do you decide? I always think about readability. So if you need lots of space to get all of your x-axis in, you want it this way. But if you need more space for the y-axis, you'll put the y-axis here. Okay? You look at your range of values, and say, all right, how do I divide it so that I get all my range in here and here? All right, so if you have a narrow range of x values, probably go here, and the y's will go there. And then you want to use as much of your axis, each axis as possible. Right, so you're already thinking about that when you think about orientation. And then when you lay in your grid, then you say, all right, that'll get all my x values in there, right? That's a waste of space. Why don't you like double your major tick marks and get in that much space? And then use as much space here on that one. So if you have several copies of that of the grid, you can play around with it, make mistakes, and throw that away and try again. But if you practice it enough, you sort of get a feel for it, and you can do it the first shot. But if this is the first time you've ever drawn graphs, then I expect you'll mess up one or two of them and have to start over. Okay. So once you've decided orientation and you're using maximum space, then you say, all right, so in that process, I say, how many minor tick marks do I need? Right? And that enters into that decision also. And then you finish labeling. Let's see. All right. So I think we covered everything that you need. Orientation, use maximum amount of space, decide on your units of measure, labels for the axis, major and minor tick marks, title, and then you can draw your graph. All right, so if this one is volume liters for the curve, what would the units be for the straight line? Right? They wouldn't be the same, right? When you take the reciprocal of a number, what do you do to the units? Same thing. Take the reciprocal of the units too. So if you have a value for volume and you take the reciprocal of it, if this is in liters, that's equal to liters to the -1. It's reciprocal liters. Okay. So when you set up your graph for the straight line part, then this will be liters to the -1. Okay. Now, if the question is, what volume would I get if I say pressure 6 atmospheres? Right? Go up here to that straight line. You go across here. So what value do you get over there? You get a value in reciprocal liters. But it said, what's the volume? Not what's the inverse of the volume. So once you got that value, you take the inverse of it, and that's your answer. Or what if you go backwards? What pressure would I need to get that volume? So if it gives you a volume, you take the inverse of it, find it here, go over to your line, drop down, there's your pressure. Okay. So don't lose track of your units when you're interpreting your graphs. Okay, let's see what else. There is a required section and a bonus section in this thing. And the bonus section can be a little hairy, so if you don't have enough time, then just forget about it. Or some of my students go into the bonus section and just try to answer some of the questions rather than draw the graphs. Right? You pick up a few points that way. And when you give your answers, when there are blanks to put in answers, be sure that unless that is a pure number, a non-dimensional number, put the units in with it. Okay? How about the slope? Let's say slope of this line is going to be rise over run, right? Change in y over change in x. So change in y would be what? It's a change in reciprocal liters. So what's the change in x? Well, it's atmospheres. So the y, this divided by that are the units. But what does that mean? That means that this is reciprocal here, but this, if we pull it up here, right, if you move from the denominator to the numerator, then you change this to a reciprocal. So we would say liters 1, atmospheres -1. Does that throw anybody for a curve? Loop. It's like, what's a fraction worth? This is the same thing as x, x times 1 over y, correct? We did that before. So if this is in units of, say, meters, and this is in units of seconds down here, then this overall would be seconds to the -1. Right? So if it's meters per second, it's meters times seconds to the -1. It's kind of hard to grasp it. I understand. So you just need to be sure you put the right units in there. Let's see. All right. Any questions? Or does anybody just want to go outside and scream? Okay. So next week, you'll turn this one in and come prepared to do lab techniques. We're going to have a variety of things like measuring lengths, measuring volumes, determining densities, using a triple beam mechanical balance, things like that. So come prepared.